Welcome to the Digital Amateur Television Experimenters Night. This is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania. Amateur radio is a worldwide hobby that has many different aspects. Digital television is just one of the many modes and areas that are covered. Maybe you're interested in becoming involved in the DATV Experimenters Nights. You realise that you do not have to be a radio amateur or need any ATV equipment to participate anywhere in the world. Also participate in the night by coming up to the Queen's Domain clubrooms. Yes, right on top of the Queen's Domain in the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind doing one of the many roles during the night. We get underway with our program on a Wednesday night from 7:30 p.m. local time. We'll see you soon. This is VK7 OTC.
In today's video, we're going to take a look at how to measure
Okay, this is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania with our DATV Experimenters Night. And welcome to what is it? Number 37 for 2021. It's the 17th of November 2021, and tonight we have a little bit of Raspberry Pi, a little bit of the finishing off of the resonance segments that we've been doing, a little bit of 3.4 gig. If I zoom around here, you'll see the top of the grid pack there. And a few other bits and pieces that we've got coming up tonight. So I'm watching the stream chat channel. So if you are watching via the chat channel, please call in. Tell us who's out there and who's where you're from, where you're watching from. That's really helpful. And hello, Anthony, VK7LOG. Thanks for calling in. So we'll get underway. The first thing I'm also listening on repeater 2. So if you're on repeater 2, then please call in via repeater 2 and ask questions if you have some. Now, what I have, and if we go to let's zoom out a little bit there. Okay, we have this funny looking thing. Now, this is a Raspberry Pi case, very nice laser cut acrylic case. You can see there is a Raspberry Pi 4 in there. There's the USB-C connectors, which is the dead giveaway, and also the micro HDMI, the 2 micro HDMIs, which is the dead giveaway of the 4, and also the Raspberry Pi C, the USB-C connector for the power. So this is a little case, comes from Ultronics, and these funny little wings that stick out here are for a Vesa. So the back of a monitor or a television mount, this can screw directly onto the back of the television or the monitor as a display type PC. Raspberry Pi PC. Probably Raspberry Pi 4 is probably a little bit of overkill for this particular application, but this particular case does also fit a Raspberry Pi 3. You can see the connector cutouts are quite big here, and the form factor for the 3 is very similar. So, and also, given it's a 4, there is a little fan, a little 5-volt fan, and you can see it through there in here. There's a little fan, 5-volt, very quiet fan. You can't hear it. That blows onto the processor there, and you can see there is a heatsink on the processor that I have stuck on there with some thermal transfer tape. So all covered, shouldn't overheat. But little Raspberry Pi Vesa. This is the Vesa mount Raspberry Pi case. Now it comes in a kit. That's the kit from Ultronics. All the little bits and pieces. It is, can I just say, it is an absolute pain to get the protective paper off of the laser cut bits of acrylic, but you get there eventually. And all of the mounting hardware and everything to go with it from Ultronics. So if you're into Raspberry Pis and Raspberry Pi cases, then this is an option because you can mount this directly on the back of the monitor, and you can literally end up with a monitor computer. Raspberry Pi 4s are a quad-core processor. It can run Windows if you really want it to, and runs it with a decent amount of performance. So you can actually come up with your own little, NUC, I suppose you'd call it, which just mounts on the back of the monitor and gives you a reasonably powerful little computer. What I am going to actually use this for is, there is a wonderful application out there that's available. There are free versions of it called the DAKBoard, DAKBoard. And the DAKBoard is a little application that runs on a Pi, and it gives you the ability to display your diary, some information of the day, a news feed, whatever else. So you can have an information board actually mounted on the wall, running off a Raspberry Pi, and it's updating based on your calendar and a whole lot of other things that you can configure, weather, information, etc. So it's called DAKBoard. Runs very nicely on Raspbian, which is the Unix version for the Raspberry Pi. So that's what this is actually going to have on it. It's on a 19-inch monitor, big monitor that is will be in landscape. In portrait. So the long ends of the monitor will be vertical. So that's what I'm actually using it for, and it's this literally just screws onto the back of the case. So Raspberry Pi Vesa cases, worth a bit of a look. Now, resonance, our last segment around resonance. Okay, quick reminder, resonance is that special condition which is where you get increased amplitude due to a force being applied to a system, and the system can be almost anything. The example I've been given is I have an antenna at home. When the wind blows in a particular direction with a particular strength, that particular antenna, which is a disc cone, a UHF-VHF disc cone antenna, starts to sing at a particular frequency. And it only happens to be that frequency, that wind direction and that wind energy that puts enough energy into that particular system for it to start to resonate, and resonate enough that you hear an audible tone coming out of that particular system. So that's we call that its resonant frequency. So last week we talked about crystals, and I finished off by saying we'd have this week a little bit. I finished off with a and we'll zoom in here because you okay. So this is a ceramic resonator, very similar use to a crystal, but the question was asked, what's the difference between a ceramic resonator and a crystal? Well, there's actually not that much difference. It uses exactly the same principle, namely piezoelectricity, where you have two plates with, in the case of a crystal, with a quartz crystal cut in a particular way between those two plates. But in the case of a ceramic resonator, or what they call a dielectric resonator, instead of it being crystal, it's actually a piece of ceramic dielectric. So it's an insulator cut to a particular size so that when you apply an energy through these connections to it, and that particular energy is at a particular frequency. In this case, this is a 3.58 megahertz ceramic resonator. This is a color burst ceramic resonator used to be used in color televisions. This particular one starts, that ceramic or dielectric starts to resonate, so the energy enters the dielectric. Because of the size of the dielectric, it starts to set up standing waves and exhibits, very similar to a crystal, it exhibits a stability at a particular frequency, and in this case 3.58, and we'll show that in a short while on the NanoVNA. So it's very, very similar to a crystal. However, these are much cheaper to manufacture than a crystal, and so these have been certainly for digital electronics been used in preference to crystals for quite a while. And you'll find ceramic resonators in place of crystals in quite a few digital applications, and in this case color television applications. So that's a ceramic resonator or a dielectric resonator. So what, and I also said last week what we would do, because I hadn't made up the little jig for the NanoVNA, and so I managed to make this up today, and I'll show you. It's pretty simple. In fact, it's incredibly simple. This is two little SMA connectors, so 50 ohm SMA connectors. There are a few tracks cut into here. If I pull the crystal out, you'll notice that there are a couple of these are IC socket, machined IC sockets, so they're the high quality ones that come to each end, so you can do a series check, a parallel check, or you can go to ground on one of them. There's one that's connected to the ground here, or you can put in a capacitor in here if you want to, or an inductor to pull the crystal to a particular direction. And this goes off to the S11 and S21 ports of the NanoVNA. And the reason why it's this spacing is if I use dual-ended connectors, so this is where there's two males, I can actually get rid of these particular cables and literally put this particular item straight onto the end of the NanoVNA, which gets over the fact that you've got to calibrate for these particular cables each time you use them. So what do we use, and how can we represent and find out what the frequency of a particular crystal or resonator is if say the label wipes off of it? Well, what you can actually do with a NanoVNA, and I'll just do a bit of a quick setup here. We've got, I'll show zoom in a little bit here. So what we're setting it up for, we want we want channel 1, so we'll set it up for trace 1, and we'll make trace 1 format, we'll make trace 1, we want a phase on there. We want, go back and back, we want trace 2, which is channel 0, channel 0. Hang on, we want, I've got to get this right. Trace 0, there we go. Now, we want trace 0. We want the format to be phase. Great. We want back, trace 2, trace 1, no, we want trace 3. Trace 3, we'll switch off trace 2. Trace 3 is also channel 1, which is the S21, which is what we want. And we'll go back, and we'll make that format log magnitude. Okay. Go back. Display, trace 0, trace 0, okay. Format, phase. Cool. Now, we need to set the frequency that we're scanning on, so stimulus and start. Now, we know the frequency of this particular crystal, so we'll make it, we'll scan from 7 to 8 megs. That's phase. Okay. Cool. Okay. And in fact, what we might do, just so for screen, if we make it 7.2 megs to 7.4 megs, let's make it 7.5 megs. That's a bit better. Okay. So what we're looking at here, and I've got the 3728. So that's a UART frequency for those who have done anything with microcontrollers. That produces the right frequencies for a universal serial port for a UART. And so what we're looking at here is the yellow line is the phase, and we'll talk about that in a sec. And then the purple line is the, let's go back. The purple line is the insertion transmission coefficient, the log magnitude of it, showing the series impedance. So let me get my pointer. The series impedance of the series frequency of this crystal, and this one down here, that's almost 0. So it is very low impedance. This is the parallel frequency. So this is the series frequency of the crystal, and this is the parallel frequency of the crystal, which shows that parallel frequency shows a very high impedance. And if we move the cursor along to the series frequency, that's about the top. We're looking at 7.3, what is it? 7.371 megahertz, and if we go to the parallel frequency, we've got 7.386 megahertz. So that's giving us literally the range, depending on the circuit you use with the crystal, is the sort of range that you can actually get out of this crystal. Not very much, but in a series type circuit, low impedance series type circuit, you could get 3.368, sorry, and then in a parallel type circuit you could get slightly higher than that, which is 7.386. Now, what's happening to the phase, which is this yellow line? Up here at our series, you'll notice that just before it, we're at, this is 0 degrees, this is minus 90. So we're at minus 90, and as we go through the series, you'll notice it flies up to plus 90. So it goes through 0 and goes to plus 90. In between the series and the parallel, it stays at plus 90, and then at the parallel frequency, it drops back to minus 90 degrees phase. So that's the phase difference from both the series and the parallel frequencies that this particular crystal is capable of. And hello Sean, and hello Tassie T, and hello Richard, so who's on our stream. So you've come in at the demonstration phase. So that's this particular crystal. Now, I thought what I would do is we'll have a look at how different the resonator is, and what the sort of different characteristics of a resonator is, if there is any. Now, the resonator is quite a different frequency, so what we've got to do, start frequency is about 3.5 megahertz, and the end frequency is what we will do, 3.6 megahertz. Hang on, that didn't... 3.6 megahertz. Oh, and the start frequency is 3.6. Let's suppose 3.5. No. 3.4. Let's go a little bit more. Oh, there we go. Okay, start frequency is 3.3. That's a bit better. Now, much wider. What we'll do is go from 3 megs to 4 megs. Different characteristic. Quite different characteristic with a resonator. So what we're talking about here is, now, ceramic resonators, they will hold their frequencies quite well, but you've got to drive them fairly hard. Digitally, that's usually not a problem, because you drive them with hex inverter gates. That's how they're usually used, and that's how you get that phase difference between the input and the output, so there's a bit of sort of negative feedback going through, and it keeps it going. But what we're looking at here is, we're looking at the purple, which is the frequency, if you like, much wider peak at the serial frequency, and a much sharper parallel frequency. But you'll notice that there is a few little artifacts here on the other side. And this parallel frequency doesn't go anywhere near as higher impedance as the crystal. So you'd probably say that a resonator is a lower Q or a lower quality type device. Much broader peak on the series frequency up here. So quite a different characteristic. You'll notice that it goes from a negative phase difference. As soon as it hits its peak, it goes up to a positive and much higher here. So these are 90. Hang on, let's go back in frequency. So our series frequency is 3.43 and our phase is 173 degrees. If we drop down here, this goes back to about minus 127 odd, then jumps up to 173 and then through to the parallel frequency. That plateaus off and goes from about 128 degrees phase to down to about minus 128, and then you'll notice in here there are a few little phase changes up here in these other little artifacts at the towards the 3.8. What's this? 3.7, and then down. This is the parallel frequency, which is 3.65, and then we get to 3.58, which is about in the middle here. So it's interesting that the actual frequency is around about the centre, which is what you'd expect. It's somewhere between the serial and the parallel frequencies that you're applying to the resonator. But you can see quite a different profile and much less sharp series and parallel type frequencies as compared to the crystal that we just looked at. So serves the same purpose, but slightly different characteristics, and what you'd expect, because there is certainly to get a resonator and to create a resonator and build a resonator doesn't take anywhere near as much manufacturing as a crystal. So lower Q device, slightly different characteristics, and that's how you use the NanoVNA to measure a crystal, and in fact a whole lot of other devices. That's a little universal jig. And one of the videos that I've got tonight is the W1AEW, one of the videos for our RF viewers tonight. Please have a look at W1AEW's huge series of YouTube videos, because he actually talks about exactly this. This is where I got the design for the jig, and goes through and does the case capacitance measurements and all sorts of things. I'm shortcutting this particular measurement, but there's a whole lot of other things that you can actually do and use these jigs for. But NanoVNA, again, this is about a $100 device, and you can do some absolutely fascinating stuff with these devices. So and if you have a crystal or a resonator that you don't know what the frequency is, what you would do is set the NanoVNA up for quite a wide sweep, and then narrow it down. Keep narrowing it down until you and as you narrow it down, the 101 points that this samples on, you get much higher and higher accuracy on the frequency of the device that's under measurement. So you just keep narrowing that start and end and then stop frequency down until you realise somewhere between that series frequency and that parallel frequency, you're around about the middle, and that's what the device was designed for. So that's how you measure unknown crystals or resonators. So to a reasonably high degree of accuracy. So you'd then be able to put that into an oscillator circuit and actually lock it to the frequency that you're wanting if it's between that series and parallel frequency. So that's how to use a NanoVNA with those resonant devices, resonator devices. Oh my goodness. Okay. Okay, that's if you have a NanoVNA, make sure you check the NanoVNA Saver software. It lets you run the VNA from the PC, yes, and see everything on a big screen. And you're spot on, Sean. In fact, I have a NanoVNA version 4.2, I think it is, on its way to me, which is the latest version, and actually goes to, I think the third harmonic is 3 gigs. So almost to our grid packs, which are sitting in front of me, almost there, but not quite. Now, what I thought I would do is just very quickly, how do you then use a crystal? So crystals are great, but by themselves they really don't mean much at all. There are quite a few oscillator circuits that are out there. Now an oscillator, all an oscillator is it uses a wonderful principle which, okay, now this is we're on Ian Redpath's book again. I keep going back to this. This is how I learnt amateur radio. Oh no, wrong way. Oh, that's better. So an oscillator uses a feedback principle. Now all the feedback principle is you've got a little bit of amplification, which is what this triangle says. There is a phase change from the input to the output, and the sum of the output is then fed back into the input, and what that does is supply the energy for this L and C circuit. So this is the time constant, this sets your frequency, and this amplifier supplies the energy to that supplies the capacitor. That charges up, it then exchanges it with the energy in the inductor, which exchanges it with the energy in the capacitor, and it sits there with the amplifier supplying the energy in this circuit, and it, dependent on the value of C and L, determines the frequency at which this oscillates at, and it literally sits there and keeps going round and round at the frequency that you actually want it to go round at. Now this is an L and a C, so an inductor and a capacitor. If we replace one of these components with a crystal, and in most cases it's the inductor that we're replacing, then what you end up with is a crystal oscillator. Now if we go a few pages further on, and there's a whole lot of different types of oscillators. We've got a Hartley oscillator, and the key about a Hartley oscillator, actually, sorry, I'm going to go backwards a page to show you what the differences are. A Hartley oscillator uses a tapped inductor to set the feedback that keeps it oscillating. Then we've got a Colpitt's oscillator. Now a Colpitt's oscillator uses a very similar circuit, however it's the capacitors that determine the feedback and keeps it in oscillation. And then we've got the Armstrong oscillator. Now the Armstrong oscillator, and I think on the next page, here we go, the Armstrong oscillator, instead of using it still uses the L and C to set the frequency at which you want the oscillations to happen at, but what they actually use is a transformer that is controlling the feedback in the circuit to keep it oscillating at the particular frequencies that these set. So we've got the Hartley, the Colpitt's and the Armstrong oscillators. Now there are a whole bucket load of others, the Clap oscillator, the Sealer, the Vaca, there's a Pierce oscillator, etc, etc. Now they're all variations on a theme, on a theme of either a Hartley, a Colpitt's or an Armstrong oscillator. Now if we introduce into these oscillator circuits, in the case of a Colpitt's, instead of there being an inductor in here, we replace it with a crystal, then it's the crystal is the determining factor, and in a Colpitt's it's these capacitors that determine the feedback in the circuit, and what it's doing is exchanging the energy between the crystal and these capacitors and sets it up in a really high stability arrangement. And then there's a little oscillator here, and you'll notice the output of this transistor, this is a common emitter arrangement, the output, which is the collector here, this is the output here, goes out through a bypass capacitor. The output, there's a little feedback path here back to the input through our little resonant circuit. So this is the feedback path through our frequency determining components, and this is this controls the amount of feedback. So this is our Colpitts oscillator that is now crystal controlled, so it's much more stable. This is a FET Pierce oscillator, very similar, and you'll notice that the crystal is actually the feedback path. So very interesting little arrangement here. There's a choke bypass up to the supply, and then we've got an Armstrong oscillator. So an Armstrong, the key thing about an Armstrong oscillator and what makes it an Armstrong oscillator is this transformer that is the thing that determines where the feedback and how much feedback there is. What you've got is a tap on this transformer. You'll see its own separate little tap off the supply that comes in through the crystal round here, and it is inductively coupled as part of this transformer, and it's a FET arrangement here. So this is how you introduce the stability with the crystal. So these are the various crystal oscillators that's how you introduce a crystal and make it a crystal controlled oscillator and give you the stability that crystals give you in those particular cases. So there you go. Oh, okay. Yes, thank you, Sean, for answering Tassie T. And yes, if you're transmitting, you do need a license. But if you're just receiving, well and truly, you can receive to your heart's content. Don't need a license. Of course, there are some laws around receiving certain frequencies, like mobile phone frequencies, and a few other things. There are some laws against that you can't listen to that sort of stuff. But on amateur frequencies or other broadcast frequencies, certainly you do. So there you go. And 3 cheers for Anthony, who's doing his advanced license course at the moment. So excellent. Well, I hope you've got a little bit of an idea about the difference between a Hartley, a Colpitts, and an Armstrong, and the reason that they are actually that type. There used to be questions in the exam, I don't know whether there still is, where they would give you a little circuit and then the multiple choice questions to say, is this a Colpitts, Hartley or Armstrong oscillator? And the key thing there is Hartley is tapped inductor, Colpitts is capacitor controlled, and Armstrong is transformer controlled. So that's how you remember it. So I hope that helps, Anthony. So what are some of the other different types of resonances? And this is we'll finish off at this, because there are some absolutely fascinating bits of other resonances that are all around us in the world. The pendulum on a clock is a classic example of a resonant system. The clock provides the energy into the system, so if it's a wind-up clock or it's an electric clock, and it supplies the energy that pushes the pendulum, and then based on the length of the pendulum and the weight at the bottom is how far it goes. And what you do is you set it so that it is doing 1 second at each swing, and it's all set up so that it does that. The clockwork mechanism, or the electric part of the clock, is supplying the energy just to kick that pendulum a little bit, and it'll sit there, and once you've got everything in balance and everything tuned, it sits there and it does that and can hold pretty good time. And in fact, a lot of the time standards that the PMG used to use a long time ago were large pendulum clocks to do all of that sort of thing. So that's a good example of resonance. It's 1 swing per second in the case of a clock. Your vocal tracts and your vocal cords, that's why we all have different sounding voices. It's because of the characteristics of our vocal tract, which is a whole lot of our vocal cords, which we push air through and they vibrate, and because of the resonator, which is your head, and the characteristics of your skull and the characteristics of your mouth and your palate, etc., is why you sound the way you sound. And that's the resonance of the system, which is your head. So that's a good example. Now, you may have seen wine glasses quite high quality wine glasses. Now I was I was going to bring one with me, but I totally forgot about bringing it with me, so I apologise for that. But if you just wet your finger, you can get a high quality wine glass to sing. And there are lots of different types of instruments. There's a thing called a glass harp, where it's got a whole lot of different loops of glass that are all tuned differently, and you get each of those rings to actually sing. Quite a eerie sound, bit like playing a saw blade with a violin bow. It's that sort of sound. And there's a wonderful Mythbusters episode about a woman's voice, very high voice, being able to smash a wine glass, and I think they dispelled that particular myth. But anyway, now the NBN fibre to the node and also fibre to the home relies on a passive optical system that relies on optical resonance in cavities. And if you have a cavity of a particular size that you put, and light is just electromagnetic radiation, and you put it into this cavity, and the cavity is tuned for a particular frequency, for a particular light frequency, then what that cavity sets up is a whole lot of little little standing waves within that cavity. And what you can actually then do is get a separation of longitudinal waves and transverse waves. And so what you can actually do is inject into that cavity two different data streams, which are then transferred onto the fibre together. But because one's a transverse wave and one's a longitudinal wave, they don't interfere with each other, but you double the bandwidth of that particular fibre. So there are a whole lot of optical resonance methods that are actually used, and they're being used in the NBN network all the time, and also Telstra's network, and all those companies and organisations that run fibre around the place. There are some pretty tricky methods used to increase the amount of data that you can put over those fibres. Just phenomenal. Now, our solar system, thank goodness, has a whole lot of resonances in it. The moons that go around Jupiter, our solar system, all the planets going around the sun, they are all fixed in a particular orbit based on the characteristics, and these are interstellar type, constellational type sized resonances, but they are all fixed in particular orbits because of those planets of particular sizes have particular gravity. They act and interact with each other, and they have formed the what we know as the solar system. So there's a whole lot of resonances. On Earth, whenever there's a lightning strike, we get what's called a Schumann resonance, which is the fundamental frequency of a Schumann resonance is 7.83 Hertz. So really, really low. Challenge anyone to hear that. You'd probably feel it more than you'd hear it. But Schumann resonances, and I've got an RF video after this about Schumann resonances. There's a little talk that was given on it, which is very interesting. Your microwave oven. Your microwave oven usually uses a magnetron or a klystron to generate its microwaves. The way that they do that is through both a klystron and a magnetron use resonant cavities at the frequency at which they're generating to generate high power microwave frequencies. So they use what they call cavity resonators, which is fascinating. And also, if we go the other scale, we've gone to the universal scale. If we go right down to atoms, there are electron spin resonances. So this is the electrons going around the particular atoms that they're associated with, and there is nuclear magnetic resonance, and an MRI machine, magnetic resonance imaging. So what they are doing is putting large amounts of energy into getting your cells to actually do things, and then measuring that back out and imaging that so that they can work out what's going on within you without having to actually open you up. So MRI machines, magnetic resonance imaging, is using those resonances at the atomic level to actually then reflect that energy back into the machine and be able to image particular parts of your body that are being scanned. So resonance is all around you and all encompassing. So there you go. So that's where I'm going to finish resonance. If there are any questions, please shoot them through, and we'll see what we can do. Now, I just wanted to go on to. I keep banging on about 3.4 gigs, and then if I head round here and unscrew this this beast, we can zoom in. Now, a group of us are playing with 3.4 gigs right at the moment, and what you're looking at is from Spook Tech, which is VK3 TWO Tango Whiskey Oscar. This is a 27 dBi grid pack antenna and feed, and you can see if I turn it around, here's the feed. This is very similar. You'll probably remember these antennas on 2.4 gigs, Ostar antennas, which were all pointed at Mount Wellington on 2.4. Well, this is a 3.4. 3 to 3.4 gig, I think, is the range that this particular antenna operates at, and you'll see that this box here is the SG Labs 3.4 gig transverter. Comes out at 70 centimeters and converts up to 3.4 gigs, and you can see it's directly connected to the feed in the back there, so there's very little loss of the through that, and it's just sitting on a resource tip shop lighting tripod. And that's what we're using. We use a 70 centimeter either handheld, or I use an IC705 with this on 70 centimeters, and we all point at Mount Wellington, and it does a sterling job. So we're looking to Rex has been able to get 23 on 23 centimeters, and we're looking to get 9 on 9 centimeters, which is what 3.4 gigs is 3.4 gig wavelength is 9 centimeters. So we're looking at getting 9 on 9 on 9. So that's the antenna we've been using. We now have everybody, I think, in the south who has 3.4 gig capability has the 27 dBi antennas, and we are getting 5.9 plus signals, all pointed at Mount Wellington, or we have tried pointing at Mount Rumney and getting similar results, and that's from Richard out, and I think Richard's on tonight. Richard out at Tea Tree, Alan down in Blackman's Bay, and Steve at Newtown, me at South Hobart. Now Murray will be another one. Murray's out at Lauderdale. So we've got a good spread of 3.4 gig operators around the place. So in 2 weeks' time, we've got the VHF and above field day, the spring field day on the 27th and 28th of November, and there's a whole lot of us who are all heading out into the wilds of Tasmania to operate VHF and UHF during the spring field day. I did realise that if it wasn't on the 27th and 28th of November, it wouldn't be spring anymore. That's actually the last weekend in spring. And then in January we've got the summer VHF UHF field day as well. So there will be a number of us operating on 3.4 gigs for that particular spring field day. Now I've got something a little bit funny here. I hope people won't take too much offence to this. But I got a delivery today, which the Australian Research and Space Exploration Organisation, or otherwise known as ARS, that's one small leap for men and one giant leap for down under. So this is a funny play on words now that we have a space agency. Now this actually isn't the official space agency, but it's a bit of a play on to explore an unknown, the deep unknown. So some of my Christmas presents arrived, which is in the box, is the mug, the ARS mug. So that's the Australian Research and Space Exploration Organisation. So very nice, and they have quite a bit of merchandising if you go online. Probably you might have to be careful putting ARS into Google, but if you put in the Australian Research and Space Exploration Group, you probably will come up with the particular items you're looking for. So anyway, that's our show for tonight. Any questions from our audience, either streaming or our repeater 2 audience? And on cue, there you go. There's repeater 2 ident just coming through. So I'll just hang. That should make your coffee mug a black hole. Oh, very good, Anthony. Yep, that'll be about right. So, cheers to that, Anthony. Very good indeed. So, so anyway, we'll call it quits at that. We'll have another program next week. Now, just before I go, quick few reminders. Our presentation night for December, on December the 1st from 7:30 p.m. is Paul Daniels, VK0 PD, and VK2 something. Now Paul's just come back from Antarctica, from Casey Station, and he's agreed to give us a bit of a talk on his experiences there. So that's on Wednesday the 1st of December from 7:30 p.m. up here on the Queen's Domain, and we will be streaming it. Our Christmas activity, Reese Christmas activity, is our BYO barbecue for the afternoon group for the WAGs on the 15th, and then a repeat of it for the DATV night on the 15th, that night from probably 6 p.m. onwards. Our AGM date, 6th of February 2022, and our open day, now our open day was advertised as the 16th of February. It probably is going to be moved a little bit earlier, maybe the 30th of January. So we've just got a few issues with that particular date. It was originally the 16th of January. 16th of January, that was it. But it's probably going to be moved a little bit later towards the end of January. So, but watch the broadcast and the weekly emails that come out. So, so that's our show for tonight. Our videos, there is video on digital phase lock loop frequency synthesizers. So this is taking the resonance concept to another level. There is a little video on the Schumann Resonances, ceramic and crystal oscillators and resonators, and also the video from W1 AEW on measuring crystals using the NanoVNA. So it's where I got the technique for using the NanoVNA from, and he goes into that technique in a lots more detail. So well worth watching that. It's about 30 minutes, half an hour, and it shows a whole lot of other techniques to actually measure the frequency as well, and finishes off with the NanoVNA method. So So that's our videos for tonight. Be another DATV night next week with a whole lot of other new stuff, and there won't be any resonance anymore. So we've finished our resonance section. So there's probably a big sigh of relief out there. Anyway, we'll follow up and see you next week, 73, and wish you a good night and a good rest of the week. Cheers.